Okay, so let's talk about some property of context-free languages, and this is going to be a little bit of, a swing because we will have good news and bad news. So let's start from the bad news. So let's see an example of a language that is not context-free language, and this language is just A to the n, B to the n, C to the n, right? So intuitively, somehow you can count with context-free languages only once. If you have to count in 3 times simultaneously instead of 2, then you cannot do it with context-free languages. This is a very hand-wavy. So showing that this A to the n, B to the n, C to the n is not context-free language, it's kind of outside what we want to cover here, but in fact the proof appears in the supplemental, so you're more than invited to have a look and understand it. It's not very complicated. Essentially, it relies on the fact that when you have a grammar, if you're generating a very long word, you must use the same variable twice. And the problem is that if you're using the same variable twice, then you can do it repeatedly, and this creates some kind of a repetition effect. And this repetition effect, you can essentially repeat things in 2 places with context-free languages, not in 3 places. And then you do some case analysis and you get that this language is not context-free. And this would be very important because equipped with this knowledge now, we can prove that context-free languages are not closed under intersection. And the reason is because consider the language A and B and C star, right? So this is definitely context-free, right? Because you can just go to SSC or B, and B just goes to A, B, B, or epsilon, right? So if you think about it, the language of this grammar is exactly what's written above. Similarly, it's very easy to generate the language A star BN CN, right? Essentially, I would leave to you as an exercise to do this grammar. It's very similar, it's symmetric. And then look on the intersection. The intersection is exactly the language A to the N, B to the N, C to the N, right? Which by the previous slide, we know is not regular. We know it's not context-free language, which means that context-free languages cannot be closed under intersection, which is very sad news indeed. Okay, let's think about the positive news. So we're given 2 grammars, G1 and G2. Let's assume that they are disjoint as far as the variables, but they're over the same set of terminals. And the claim is that CFL are closed under union, and they are closed under concatenation, and they are closed under Kleene star, right? And all those 3 things are easy, so let's prove them one by one. So closed under union, well, you just generate a new grammar with a start state S that goes either to S1 or S2, which you just take the rest, and you copy the rest of the grammars, right? G1 you copy verbatim, and G2 you copy verbatim, right? So this is the new grammar. And what strings can you generate? Well, you can generate all the strings you can generate by G1, and you can generate all the strings of G2. Namely, the language of this is exactly the union of the 2 languages. So closure under union. Next one is closure under concatenation, which is exactly the same thing, right? S goes to S1, S2, where S1 and S2 are the 2 start symbols of the grammar of the 2 languages, and concatenation is immediate, right? Again, you're copying the grammars of G1 and G2, and this is the new grammar, right? And you can generate any string you want for the first language by deriving S1, and then you can generate whatever string you want for the second language using S2, and then you have to concatenate them, and you generate S from this, so this is concatenation. And Kleene star is, of course, also very easy. You just goes to S1, S or epsilon, right? Well, and then we have G1, the grammar for the first language, right? So this grammar with the start symbol S generates L star, right? You can either go to epsilon, so you get the star thingy, or you generate as many copies of words from G1 by going to S1. And that's it. So we have closure under clearly star. So this is already a pretty good news, because first it means that now it's very easy to replicate regular expression. Every regular expression, you can generate a context-free grammar that generates it. So in particular, this gives us a second proof that regular languages are in fact also context-free languages. The other proof was the one from the previous section that did it by direct reduction from DFA. And the second interesting thing is, of course, that if you look on regular expressions themselves, you write down regular expressions are generated by context-free grammars, which is an interesting tidbit. Okay, let's go back to bad news. So context-free grammars are not closed under complement, and the reason is because let's assume they were closed under complement, and now think about the following expression, right? So this is just, we complement L1, we complement L2, we take the union and we complement it. So context-free languages are closed under union. So if they were closed under complement, this would just be L1 intersection L2, but we know that there is no closure under intersection. So it's impossible that it would be closed under complement, because that would implies that CFLs are closed under intersection, which we know is false. So they're not closed under complement. So context-free languages are closed under union, concatenation, and star, but they're not closed under complement and intersection. Okay. It turns out that one can show that, in fact, if you take a CFL and intersect it with a regular language, okay, then this is still CFL. So intersection is closed if you intersect CFL with a regular language. The proof is essentially a tedious extension of the argument seen in the previous section of converting a DFA into a context-free language. Essentially, you have to simulate the DFA while doing the context-free language in the same time. We will not show the details here. Just take it on faith. And that's it for now.